Alright, so here we see question number 5 from the 2008 exam. We're going to look at some first ionization energy stuff, some periodicity things, and some Lewis structures. So here we see, using principles of atomic and molecular structure and the information in our table below, answer the following questions about atomic fluorine, oxygen, and xenon, as well as some of their compounds. So here we see the first ionization energies, kilojoules per mole. So, of course, first ionization energy to remove the very first electron from an atom. And hopefully remember, in the gaseous state, because that'll be important here, write the equation for the ionization of atomic fluorine. And so I've got atomic fluorine, not a fluorine molecule, just F in the gaseous state, becomes a +1 ion in the gaseous state, and it lost an electron. So hopefully you remember when we did talk about that, the ionization equations. Alright. Account for the fact that the first ionization energy of fluorine is greater than that of atomic oxygen. Discuss both atoms in your response. Why would fluorine require more energy? And what you should do right now is look at your periodic table and notice that oxygen and fluorine are next door neighbors. They're both on the second period, both have electrons in the same valence shell. But what does fluorine have that oxygen doesn't? One more proton. So for both, an electron is being removed from the 2p sublevel, or the second energy level. Fluorine has one more proton than oxygen. Zeph. It has a greater effective nuclear charge. Or, like I said, you could just say it has a greater Zeph. And so more energy is required to remove that electron because of the greater attractive force. Now, that's a little wordy, but, showing you got to discuss both atoms, so we need to know that for both, where the electron's coming from, and that fluorine has one more proton than oxygen, so it has a greater Zeph. Now predict, will the first ionization energy of atomic xenon be greater than, less than, or equal to fluorine? Again, you got to look at where xenon is, and xenon is a noble gas, but way down the group. In fact, the electron being removed from xenon is in the 5p sublevel, from the 5th energy level, compared to the 2nd for fluorine. So if you said 5th level, 2nd level, that would be okay. 5p sublevel, 2p sublevel, a little more accurate. But obviously, the electron being further from the nucleus experiences less Coulombic forces of attraction. So it would require less energy to remove that electron from xenon. Therefore, you would expect a lower first ionization energy than fluorine. Okay, distance, got to look at that. An electron further away from the nucleus, less Coulombic forces of attraction. Use that phrase, please. And so we would expect a lower first ionization energy for xenon. Alright, some drawings now. Xenon can react with oxygen and fluorine to form these two compounds, XeO3, Xe4. Draw the complete Lewis electron diagram. So first, make sure you know how many electrons. XeO3 is 26 valence electrons. XeF4 is 36. Xenon, if you remember from our labs, love to be in the center. So if I put xenon in the center, 3 oxygens around it, single bonds, put in all of oxygen's lone pairs, and then there's 2 electrons left over, which would be on xenon. Everyone has a octet rule obeyed. That looks good for XeO3. So with XeF4, put the 4 fluorines around xenon, and here, remember, xenon is definitely capable of breaking the octet rule, violating the octet rule. Fluorine will not double bond, so the two lone pairs, the 4 extra electrons to make 36, would easily be placed on the xenon and violate that octet rule. So now, based on our drawings, the geometric shape of XeO3. I've got a central atom, 3 atoms around it, and a lone pair. That is a trigonal pyramidal situation. If there were 4 atoms around the xenon with no lone pairs, that would be tetrahedral. But the lone pair squishes the other atoms down, makes like our back scratcher, if you remember from our lab, building of molecules. Trigonal pyramidal. Now this question was from an earlier exam, so I doubt they would ask this because we're only supposed to know orbital hybridization up to sp3. But with the xenon 4, there's 6 domains around the xenon. 4 atoms, 2 lone pairs. And so the hybridization would be sp3d2. S plus 3 p's plus 2 d's adds up to 6. Again, on our newer exam, they would probably only ask us for hybridization up to sp3. So you could expect maybe from a tetrahedral, or like this xenon over here has sp3 hybridization because there's 3 atoms and a lone pair. Last part, predict whether the XeO3 molecule is polar or nonpolar and justify. Well, anything with xenon is going to be polar. That's just whether it's reacting with fluorine or oxygen. That's pretty much the only 2 things it will react with. It's going to be a polar situation. This shape, trigonal pyramidal, is not symmetrical. There's 3 polar bonds that won't cancel out. Your tetrahedral would, your linear would, trigonal pyramidal no. So I would expect this to be a polar molecule. Okay, the XeO bond is polar. The shape means that dipoles will not cancel out, or you could say because of the asymmetrical shape or the shape not being symmetrical, this molecule will stay polar. In fact, they reinforce creating a dipole moment, but that's added stuff you wouldn't have to put there. Your justification would be because the shape is not symmetrical and your dipole moments would not cancel out. Alright, hope this helps. See you soon.